Back in the 50s, where researchers were still figuring out how to make the internet work, they faced a big challenge. That's finding an automatic method to help information take the shortest path from one device to another in a network. This is slightly different from the classical shortest path problem because, in this version, no device has a complete view of the network, but only its local neighborhood. It's like a distributed version of the shortest path problem, where each device partially solves the problem. It can be understood as the following riddle. Suppose you have a group of people in different locations, where each guy can only communicate with his neighbors. They need to collaborate to ensure that a message is delivered from a sender to a receiver as quickly as possible. Back then, these two researchers called Bellman and Ford came up with a clever solution. It's called the Bellman and Ford algorithm, and it focuses on finding a shortest path between 2 points in a network. Hello, I hope you're doing well and welcome to AliGorithm. In this video, we'll present Bellman and Ford algorithm, we'll discuss its complexity, and we will prove that it works. In my opinion, Bellman Ford is the simplest shortest path algorithm. It can even be described in a single line. Let's relax all the edges of the graph, the number of vertices minus 1 time. Relax refers to an elementary operation that involves updating the distance and the path, which will be explained shortly. But first, let's enjoy watching the algorithm in action and observe its behavior. Suppose you have two vertices, u and v, with an edge uv between them that has a cost of 2. Also, suppose each vertex knows a path from the source, S, with costs 5 and 9, respectively as shown here. Now these two vertices may have the following conversation. Hey, what's up? I know a path from S with cost of 9. Wait, I know a shorter path with a cost of 5 only. 5? That means it would cost me 5 plus 2, that's 7 to go through U. Interesting. I'll update my via and cost via variables. From now on, it's via U with a cost of 7. In general, this conversation can be summarized as follows. If the cost to reach V via U is less than the current known cost to reach V, we update V's cost via and set V's via to U. Let's consider the following network, also known as graph, with a set of vertices connected by edges or arcs. Again, let's assume the vertices are labeled with a letter corresponding to the name of the city, the ID of a router, or something similar. The edges are labeled with a cost function that could represent a travel time from one vertex to another, travel cost, etc. Now we are ready to run our algorithm. The algorithm begins with an initialization step, where each vertex is assigned two variables, via and cost via. The via variable of a vertex point to the last vertex before it on the path, and cost via corresponds to the cost of the path. Initially, since no information about any path is known, each vertex via is set to none, and its cost via set to infinity, indicating that no such path is known yet, except for the source vertex S, which is known to have a cost of 0. Now we start the main loop. The algorithm relaxes in an arbitrary order all of the edges of the graph, the number of vertices minus 1 times. In the first iteration, we may start with the edge SA. Since 2 is smaller than infinity, the relaxation procedure updates cost via of A to 2 and via of A to S, respectively. Similarly, this is done with the edge SP, and so on until all the edges of the graph are relaxed. After completing the first iteration, we proceed with the second iteration, and so on until we've completed the number of vertices minus 1 iterations, which is 6 in our case, as we have 7 vertices. Now that the algorithm has finished, we can trace the shortest path tree by following the via of each vertex. And in particular, we can trace the shortest ST path as follows. Here we can see the complete formal pseudocode of the algorithm, including the described initialization routine and the main loop with the relax procedure. The algorithm's complexity is big O of V for the initialization and big O of V times E for the main loop. That gives us an overall complexity of big O of V times E, which could reach big O of V cube for dense graphs. Now let's prove that Bellman and Ford algorithm works, meaning it finds the shortest path from S to T by the end of the process. Let's analyze the behavior. First, let's focus on what happens after the first iteration. A lot of information is propagated through the network, but none of this is guaranteed to be originate from S, since the order in which the edges are relaxed is arbitrary, except for A and B, which are directly linked to S. So, if we are looking for the shortest path using a single edge, it can be found after the first iteration. Similarly, after the second iteration, the shortest path using 2 edges is found. In general, after I iterations, the shortest path with at most I edges is found. Following this logic, since the algorithm runs number of vertices minus 1 iterations, and a shortest path can have no more than the number of vertices minus 1 edges because it contains no cycles, then the Bellman Ford algorithm indeed finds the shortest path from S to T. In the last episode, we asked whether Dijkstra's algorithm works on graphs with negative weighted edges. The answer is no. Consider the following graph. Dijkstra's algorithm starts with a vertex A, relaxes AB and AC, and fixes the shortest path via B to A, meaning it returns the shortest path AB from A to B, which is not the shortest path. On the other hand, the Bellman and Ford algorithm correctly handles this situation. Due to its repeated relaxation process, the correct shortest path SCB is returned. In general, the Bellman and Ford algorithm works fine on graphs with negative weighted edges as long as there is no negative weighted cycles. I hope you guys liked this video. If you have any question, do not hesitate to leave it in the comments below.